So I'm going to talk to you about global warming tonight. So raise your hand if you've heard of global warming. Okay, yeah, so a lot of you have heard of global warming. All right, so you know, this is a topic that is not new. You know, this basically around mid-1970s, the scientists realized that this was a problem. And what's amazing is that, you know, 50 years later, you know, we still have political leaders casting doubt on the reality of this phenomenon, which is almost laughable if it weren't so tragic. I mean, but anyway, so my job as a scientist is just to explain to you the facts. You know, what are the things that are known, and what are the things that are not known, and so that you can make up your own mind, really. You know, and it all comes down to facts. You know, we all understand that the world is round and it's not flat. I mean, we'd all agree that that was a fact. Okay, so I hope you come away from this talk tonight, you know, understanding that, you know, human causation of warming is a fact. It's not an opinion. It's not a belief. It has nothing to do with belief. It has everything to do with evidence. Okay, it's all about evidence, and so I'm going to show you some of the evidence, and let you make up your own mind. Yeah, so I always like to start this discussion with some penguins, because penguins are cute, but also because there's a baby penguin there, and I want to think about the next generation. Now, why am I thinking about the next generation? Because this global warming issue is really an issue about the next generation, or maybe 2 generations past. Why is that? Turns out that the Earth takes a long time to heat up. Basically, the ocean is like an enormous reservoir of heat. Those of you who are electronics folks will know that a capacitor is something that stores charge. Okay, well, the ocean is like a giant capacitor that stores heat. It takes about 100 years just to fill up that capacitor. Okay, so that means that the Earth itself, the Earth's temperature doesn't start rising right away when you put more energy into it. It takes time, and just like a capacitor. So it takes about 100 years for the ocean to warm up. The other thing is that when you put carbon dioxide into the atmosphere, it stays there for 100 years. Okay, so 100 plus 100, 200. Basically, when I drove my car down here to talk to you tonight, it was an electric car, but electric cars still actually emit a little bit of CO2. So let's say I emitted a pound of CO2, okay? I made a commitment to 200 years of warming from that pound of CO2. That's a pretty serious commitment, okay? So this is really not so much about our generation as it is about the next generation. That's why there's a baby penguin up there. Because this is really an intergenerational problem. The people who create the problem, us, are not the ones who are really going to suffer from it. It's more like 2-3 generations out that are really going to suffer. And that's one reason why this problem is so hard to solve, politically, because the pain is later, the gain is right now. Okay, so that is a classic strategy for encouraging people to do nothing. Just human psychology is just built to, you know, put things off if the pain is later and the gain is right now. Okay, so anyway, stop me before I start talking too much about politics. I'm a scientist. So let's keep going here. This is something you may have seen. This is the Earth's average temperature, or surface air temperature, if you will, over the past 100 and some years. And I think what you can tell right away is that Earth is warming. There's absolutely no doubt about that. These are uncontested measurements. Many different groups of scientists from different countries have all processed the data independently, and they all basically come up with the same answer. Okay, so Earth is definitely warming. You can't see the axis here because it's too small. I apologize for that. But basically, this goes from about -0.5 to plus 1 degree centigrade. So that whole vertical axis is 1.5 degrees centigrade. So I think you can see that the Earth has warmed slightly more than 1 degree centigrade in the last, say, 120 years. So that gives you a sort of a feeling for how much the Earth has warmed. Now here's a little known fact. This is something that a lot of people aren't aware of. 93% of the extra energy that has been put into the system by human-caused greenhouse gases, 93% of that energy has gone into the ocean to heat up the ocean. Only 7% has gone into things like raising the air temperature or melting ice. So you can see that the ocean is sucking up a huge amount of the heat, and the ocean is doing us a big favor by delaying the warming. But imagine what it would be like if there wasn't an ocean. We'd have more than 10 times as much warming than what we actually see. Okay, so just keep that in mind. There's an enormous amount of extra energy coming into their system right now, and most all of it, 93% of it, is getting sucked up by the ocean. All right. So, what do we know about the causes of this? Well, greenhouse gases, far and away the most important cause. This is year from around 1900 to something like 2010, and the green line shows the extra heating that's been created by all those greenhouse gases. And so what you see is that, yeah, it's going up really strongly, and that is the dominant cause of the warming. Now, you may have heard some people say, well, the sun might be causing part of it. So let's take a harder look at that. Let's be scientists, and let's look honestly at the data, see what it says. So the sun's role in heating the Earth is plotted here, and you see it goes up and down every 11 years. That's called the solar cycle. Turns out the sun has a cycle every 11 years. It flips its magnetic field, and so you see the sun's output going up and down. But basically, this is all small stuff. These are like much less than 1%. This is like these variations are less than 0.1%. And in fact, in recent years, the sun has been cooling off. So the sun, this does not explain the warming we see. Volcanoes actually have a cooling effect on the Earth. The reason is that volcanoes spew out a lot of sulfur. Sulfur, when it gets into the high atmosphere, reflects sunlight back to space. So it's acting like a bunch of little mirrors up there that are reflecting sunlight back to space, which makes our planet cooler. Yay. Okay, so volcanoes cool the Earth. There has not been any particular decrease in the number of volcanic eruptions lately. In fact, there's been kind of a lot of them actually in the last, say, 40, 50 years. So volcanoes don't really, provide an answer either. Bottom line, greenhouse gases are producing at least 95% and maybe all of the observed warming of the last, say, 60 years. Okay, so those are the known causes. So let's dig down a little bit deeper for a moment and talk about exactly why it is that gases like carbon dioxide cause global warming. It's because of this thing called the greenhouse effect. And so what the greenhouse effect is simply that the heat that the Earth normally would give off to space gets trapped. Think of the greenhouse effect as like a blanket. Gases like carbon dioxide act like a blanket. They prevent heat from escaping to space from the Earth's surface. And that is what the greenhouse effect is. It's interesting that the sun's rays themselves don't interact with carbon dioxide at all. The sun rays comes right through the atmosphere. The atmosphere is very transparent to that particular type of radiation, light. But the type of radiation that the Earth gives off to space is strongly absorbed by carbon dioxide. Does anybody know the name of that type of radiation? Infrared, very good. Somebody back there. Okay, so infrared radiation. Infrared radiation is the kind of radiation that you would feel if you stand near a really hot wood stove, right? It's just You can sort of feel it, right? And that is infrared radiation. So that's how the Earth cools off. The Earth mostly soaks up energy from the sun, and then it cools off by radiating infrared radiation back to space. And what carbon dioxide does is it intercepts some of that radiation, traps it, and it warms up the atmosphere. So basically keeping some of that heat in the atmosphere and keeping us warm. Yeah, so this is an estimate of what the warming will look like about 80 years from now. This is actually 2100. So this is a computer model, and it is basically about, the red colors here are about 4 degrees centigrade, which is about, say, 7 degrees Fahrenheit. And so what you see from this is that a lot of the continents are going to be something like 7 degrees Fahrenheit warmer than they are today. That's a pretty seriously changed world we're looking at there. Notice that the oceans don't warm as much as the continents. That's precisely because of what I told you before, that the oceans are like a giant capacitor. They just soak up heat. So they don't warm as fast as the land, just because it takes hundreds of years to really heat up the ocean. So this is a pretty seriously changed planet we're looking at. So if human beings don't alter their current, practices of burning fossil fuels and putting methane and other gases like nitrous oxide, laughing gas, into the atmosphere, we are looking at a very hot planet where rainfall patterns will certainly be different, which means things like droughts, and when people don't have anything to eat because they have a drought, they have a tendency to go to war and commit genocide and have failed states and all those kind of things. So we're looking at some really, really serious disruptions to society if we don't decide to do something about our fossil fuel problem. Let's back up a second. Let's get back to the physics here. What is it that tells us that humans are actually doing this? How do we really know this? Let's just dig down into the science for a little bit. Basic physics tells us that CO2 traps heat. This has been known since 1861. This is not exactly new knowledge. The British physicist John Tyndall discovered this, and it's been confirmed again and again and again for more than a century since then. So this is known very, very deeply. It's basic physics. In fact, our own Air Force, Department of Defense, spent hundreds of millions of dollars to really understand exactly how CO2 traps heat. And you want to know why? Because the CO2 coming out of enemy aircraft was messing with the heat-seeking missiles. And because the heat-seeking missile looks at infrared radiation, right? Okay, and so they're looking for the heat from the exhaust from the back end of the enemy aircraft, right? To make the heat-seeking missile supposed to find that heat. But it was getting messed up by the CO2 that was coming out of the engine, because of course when you burn hydrocarbons, boom, you get lots of CO2, right? So our own Air Force spent hundreds of millions of dollars to really understand how exactly CO2 traps heat. Boy, did they ever do a good job of it. So we really know a lot about how CO2 traps heat in exquisite detail. Basic physics. CO2 is just basic physics. Not new science. This is very old, established science. In fact, an interesting thing was discovered just a few years ago, which is that a lot of the scientists who worked for companies like Exxon and Mobil, those scientists back in the 1970s were doing research, and they were all, agreeing and talking about how CO2 traps heat and all this kind of stuff. So, and even the company president agreed that this is real. So the company president of Exxon agreed that global warming is real. It's caused by humans. It's caused by carbon dioxide. No dispute at all. Okay, so, so what happened? Well, here I'm going to veer off into politics for a little bit, but it seems that what happened was that around 1980, the company decided that it was in its financial interest to deny global warming. So basically, they just fired all their scientists, you know. So it's like it's not exactly the case that the science is uncertain. The science is very, very certain. Also, our neighbor planet Venus tells us something about CO2 causing warming. Why? Because Venus has a CO2-rich atmosphere. And by CO2-rich, I mean like really rich. 100,000 times more CO2 in the atmosphere of Venus than Earth. And guess what? 864 degrees Fahrenheit. It is so hot on the surface of Venus that lead melts. So it's really hot. Okay, and that's hot because of the greenhouse effect. So even if you don't believe basic physics, you just have to look at our neighbor planet Venus and you see the answer right there. Second big important fact that tells us that CO2 traps heat and that humans are causing the current warming. Precise measurements of atmospheric CO2, which were made at the Scripps Institution of Oceanography, actually, my employer, starting in 1957, showed that the concentration of CO2 in the air was steadily rising, and more importantly, the known amount of fossil fuel burning corresponded exactly to the amount by which CO2 was rising. How do we know how much fossil fuel was being burned? Well, good records are kept of fossil fuel burning because it has economic value, and so people have an incentive to keep good records of it if it has economic value, right? So it seems like if this was a murder mystery, this would be case closed, right? Because you know how much was burned and you know how much should be in the atmosphere, and then you look again and you see that indeed that amount of CO2 is in the atmosphere. So that's what we call the budget approach, basically. You know how much you put in, and you look at what's there, and if it matches, pretty good bet that that's true. This is the famous Keeling curve. These measurements of CO2 started in 1957. I was so impressed with this curve. That's why I decided that I really wanted to work at the Scripps Institution of Oceanography. So that's how I ended up at Scripps, because I was so impressed with this record. This record is sort of iconic. It really represents, in some ways, in many people's minds, sort of the global warming problem. This is what really alerted us that we had a problem. Nobody had bothered to measure CO2 carefully before 1957. So it's basically unknown before 1957, except I'm going to show you later that we can use air bubbles trapped in ice cores to go back in time. But that's when the direct measurements were first begun, right about there. So we're here at 406 parts per million. So the other way we know that humans are doing this is that carbon comes in two different flavors. Ordinary carbon is carbon-12, has 12 neutrons and protons. There's another kind of carbon, think of it as another flavor of carbon, carbon-13. It has an extra neutron. Okay, it's got 6 protons and 7 neutrons. So carbon-13 is very depleted in fossil fuel, but it's quite abundant in what you might think of as natural CO2. Okay, so you can tell between natural CO2 and sort of human-produced CO2 using the amount of carbon-13. And if we go back into the ice cores, this is an ice core, you can get little tiny air bubbles. They look like this. These are little tiny air bubbles about 1 millimeter wide. About 10% of the volume of glacial ice is actually air. It's really quite a lot of air. It's quite it's an amazing thing. And so what we do is we release these little air bubbles by melting the ice in a vacuum. So we remove all the modern air. And then once we've got the old air there, we analyze how much carbon dioxide there is in that air. And that gives us points like these squares and triangles here. So those are ice core measurements. The black line is the direct measurement by Charles Keeling from the South Pole. So these are Antarctic ice cores. These are direct measurements at the South Pole, and the atmosphere over Antarctica is basically all the same in CO2. So we can see that the ice core measurements agree well with the direct measurements from the Keeling curve at the South Pole. Where they overlap, which is between, say, 1960 and 1980. And then going back in time, before 1957, the ice cores are the only way we know what the carbon dioxide concentration was in the air. And this is what it looks like. This is from 1000 AD to 2000 AD. So this is 1,000 years. The whole Keeling curve is jammed into this little rise right here. And what you're seeing is that carbon dioxide changed from about 200 parts per million, which means that if you had 1 million air molecules, 200 of those molecules would be carbon dioxide. Sorry, 280. So you can see that it's pretty steady for most of the last 1,000 years, but around 1850, which is the beginning of the Industrial Revolution, when large-scale coal burning first started, then it started to climb and climb even more rapidly after the Second World War right here. And so today we're up at about 410 parts per million. It's going up at about 2 to 3 parts per million per year. So this is happening really fast from a geological perspective. This is all what we get from the ice cores. And here's the important part, I think. The carbon-13 concentration in that CO2 from the ice cores has been measured, and that's shown in this gold line here. So you see that the carbon-13 content, don't worry about the units right now. These are just relative changes in the ratio of carbon-13 to carbon-12. These gold points were pretty flat for most of the last 1,000 years, just like the CO2 concentrations. And then at the beginning of the Industrial Revolution, they took a nosedive, and the reason is simple. Fossil fuel CO2 is very depleted in carbon-13. So as you add fossil fuel CO2 to the atmosphere, it drags down the whole atmosphere's carbon-13 abundance. So I call this the smoking gun of human causation, because it shows beyond a shadow of a doubt that it's humans that are causing the current CO2 rise. This is not natural. If this was a natural CO2 rise, these gold points would have stayed flat. They would have stayed flat right across here to, at about minus 6.5. So, case closed. This is at this point, a jury would convict beyond a reasonable doubt. Yeah, humans are causing CO2 to go up in the atmosphere by burning fossil fuels. We see that from the carbon-13. We know from basic physics that CO2 traps heat. Ergo, humans are causing the planet to heat up. If you want to go back farther in time, it's kind of interesting. This is the last 10,000 years, but it doesn't really change the picture. Mother Nature, was keeping CO2 pretty much constant until the Industrial Revolution, when it shot up, and it's today at about, well, this is a little bit old, but it's about 410 today. So it's going up really fast. And we've only just begun. Here's the scary part. We've only burned about 1/10 of the total fossil fuels that are in the ground. So you could think of it this way. If it's gone up a little more than 100 ppm, well, if we burned all the fossil fuels, it would go up 1,000 ppm, right? So we're looking at potentially a very, very radically changed planet if we choose to burn all those fossil fuels. I want to take a little bit of a detour now and talk for a minute about methane hydrates. Have any of you heard of the idea that methane is going to come bubbling out of the tundra and add to warming? So I see some hands going up. Yeah. So I've been accused of giving a lot of gloomy and depressing information, I'm going to tell you something hopeful right now. This is kind of a scientific, hopeful story, a good news story. This hydrate is actually a form of methane, which is encased in a little cage of ice. So think of it as methane ice. It's a solid, and it is stable up, below about 4 degrees centigrade, so pretty near zero. So it's a lot like water ice, but it's a little bit different. And if you let it sort of decompose, it will give off methane gas, and that's what's happening right here. See the flame? So you can actually burn ice, which is kind of fun. You can hold this stuff in your hand and you won't get burned because the ice keeps your hand cool at the same time that the methane is burning. And so many scientists have worried that as the planet warms due to human emissions, a lot of this methane ice will melt. And they're probably right. It probably is going to melt, okay? And the worry is that melting will release large quantities of methane gas that was formerly in an ice form to the atmosphere. And we know just from seismic studies and doing test coring that there is a lot of this methane hydrate out there. Huge, like maybe as much as all the fossil fuels combined. It's not known very well. Anyway, so the worry is that global warming could cause this stuff to come burping out into the atmosphere, so-called methane explosion, making more global warming because methane is a very powerful greenhouse gas. Methane, molecule for molecule, is about 200 times more powerful at trapping heat than carbon dioxide, so very potent. And so my students and I decided we were going to test this idea that methane comes burping out of the tundra during times of global warming. And there was a natural warming actually about 11,000 years ago caused by natural processes. The ocean circulation switched on. So we decided that if this methane really did come burping out into the atmosphere, we could see it. We could see it by looking at the gases in the air bubbles in ice. So we did that. We tested this methane hydrate hypothesis by measuring huge amounts of air bubbles in ice. It took us about 1,000 kilograms per a sample to measure the methane in the ice. And what we found was that, interestingly, there was no methane that made it to the atmosphere, at least no measurable amount, at this big abrupt warming event that happened 11,000 years ago. So that is probably good news in a sense. I would say that here's the data. You can see that we were measuring another rare flavor of carbon, this time carbon-14. Carbon-14 is made naturally in the atmosphere by cosmic rays, and has a half-life. It decays about half of it in 5,000 years. Okay, so those old methane deposits, they're like millions of years old. There is no carbon-14 at all. On the other hand, other sources of methane, like cows belching and landfills, swamps, blah blah blah, those all do have carbon-14. So you can actually distinguish between the hydrates and all the other kinds of methane using carbon-14. It's just a perfect discriminant between these two different kinds of methane. And so we know that if all that hydrate methane came into the atmosphere, this is going forward in time, so this is like 11,000 years ago. And if we know that if all that hydrate methane made it to the atmospheric carbon-14 would have taken a nosedive like this. And it didn't at all. Here's the data points right here. You can see that basically nothing happened. So that's actually really interesting information. We're all pretty sure that the global warming back then, which was natural, did cause all that hydrate to melt. We don't see how it could not have. But it didn't make it to the atmosphere. That's the really interesting thing. So what could have kept it from getting to the atmosphere? It's really interesting, but it seems like there's little bugs, microbes that live in soils that eat methane. They actually make a living by eating methane. So these microbes are our friends. It seems like what happened was that those microbes actually consumed the methane that was being released from the ice before it ever made it to the atmosphere. And not too long ago, there was an accident that sort of just demonstrated this concept of methane-eating microbes basically vacuuming up methane before it ever makes it to the atmosphere. Anybody remember the Deepwater Horizon accident in the Gulf of Mexico? Yeah, so this is a terrible, catastrophic accident in which an enormous amount of methane was released from the bottom of the seafloor into the water column. It didn't make it to the surface, but just kind of about mid-depth. Well, scientists went in afterwards and measured the methane, the oxygen that was dissolved in the water, and DNA to see, what microbes might have been living down there. What they found was there was an enormous amount of DNA from methane-eating microbes, and there was a huge deficit in dissolved oxygen. What apparently had happened is that those microbes had one heck of a party. They ate up all of that methane. 99.9% of the methane released by the Deepwater Horizon catastrophe never made it to the atmosphere. Now, some of the oil, made it up to the top, but the methane, 99% of it was eaten before it made it to the surface, eaten by microbes. So I think this tells us about the power of microbes. And so I want to leave you with some sort of good news, if you will, that, maybe that methane that's people have been worrying about in the tundra, maybe that's actually not a problem. Maybe we can relax about that one, check it off the list, say, okay, that's one thing at least we don't have to worry about. And there's a bunch of other studies that are now coming to similar conclusions as the ones that my students and I came to, that looks like the microbes are our friends. They're going to sop up the methane before it ever makes it to the atmosphere. Don't get me wrong, there's a big problem with CO2, but with methane from the tundra, I think we can relax on that one. Thank you very much.